Earth Science, Landslides. And we're going to start talking about mass wasting at the beginning of this lecture and then move to slope failure later on in the lecture. Mass wasting is taking place in the picture you're looking at there. This is in Colorado. You get a house at the bottom of the picture with a pretty stream next to it and a road going there. Nice long driveway to the left. But right uphill from that house you have a great big landslide area. And question is, would you live there? Would you risk the chance of having a landslide just cover over your house in the right kind of weather conditions? Get enough big rain and it may create a loose slope there and come right down over your house. Kofi Annan, who was the Secretary General of the United Nations, said, "The term natural disaster has become an increasingly anachronistic misnomer. In reality, human behavior transforms natural hazards into what would really be called unnatural disasters." So if that house gets covered, is it a natural disaster? Well, it'll get called that, but it's only because somebody built a house where they shouldn't have, or somebody allowed water to be put in that slope above there and they shouldn't have, or the list goes on. If you look at the picture on the left, you can see where you get bare spots, and right in the middle of the picture you've seen there's a landslide that's covered over part of that city of La Conchita, California. Well, human impact is what causes a disaster. It's not the natural phenomenon. If a tornado goes through a field and it doesn't impact anybody, it's not a disaster. If it breaks up a house and it's a disaster, well, humans are what creates a disaster, not the natural phenomenon. Well, this was a disaster because in a matter of seconds, a 330-foot partition of the slope, it mobilized and flowed down and buried homes and killed 10 people. And a resident in La Conchita said, "It came down like lava from the mountains. It was explosive. There was a stick of dynamite." Which leads to a definition of mass wasting and a landslide. Mass wasting is the downslope movement of material under the influence of gravity, and a landslide is just mass wasting that happens quickly. So mass wasting and landslide is mass wasting that happens quickly. And here's the parts of the U.S. that experience mass wasting, i.e. landslides, and as you'd expect, they're in areas where there's mountains. Well, gravity is what affects material moving down slope, whereas friction holds material back. So gravity is working to move stuff down, and friction's holding stuff from moving down. An example is a playground, a slippery slide on a playground. The steeper, the smoother the slide, the faster you go. So steeper, more gravity; smoother, less friction. And here's mathematically what we're trying to show with that. Gravity has two components. Gravity is the arrow going straight down to the center of the Earth, but the two components are GS, the part of gravity that's at an angle where it parallels the slope, and GP, the angle of gravity that's perpendicular to the slope. So mathematically, you see that B is, okay. Mathematically, you see that GS, i.e. the steeper slope, is longer in the lower picture, B, than it is in A. Well, that's pretty obvious. The slope looks steeper, but what we need to do is in order to understand and measure slope failure, we need to put it in a mathematical formula. And we do that here with the GS and GP, gravity of the slope, gravity of the perpendicular to the slope. So if GS is larger, the slope is steeper, and there'll be higher gravity component on that material moving down slope. Let's look at how water affects this. if you can see a pile of sand on the left. Dry sand will slope with an angle of about 35 degrees. So dry sand, it will hold up a slope, and if you get your protractor out, you'll see that that's about a 35-degree angle from a horizontal. Well, if you put water on those sand grains, you can make that slope steeper. Well, that's why we have to have water in our sand to build sand castles on the beach. But if you put too much water in the sand grains will be forced apart and the sand will fall down. So that's why you don't want too much water on your sand castle at the beach, but you want some water on it so you can not just have little pyramids, because that's all you're going to get if you don't put water in. So cohesion of sand sticks those particles together from water. The other thing that affects slope is the size of the particles. Fine sand is 35 degrees slope. If you make the sand coarser, you can get a 40-degree slope. And if you make the sand even coarser so that it's not even sand, it's pebbles, you can get up to a 45-degree slope. Of course, you could take that logically, I don't have a picture of it, and say that's one big rock, in which case you could have a 90-degree slope, which you might get like at Old Yosemite out in California, where the rock is just a vertical rock. So it makes sense. The finer the sand, the less the slope. And here's a nice picture of a sand castle on the beach. None of my sand castles look that nice, but with moist sand you can get a nice vertical, and that's a looks like it's a moist sand, but looking at the sand it looks like it's not just a pure quartz sand. It's probably got some dirty clay and silt in it, which also helps stick it together. Notice how water saturated sand isn't going to have any vertical slope at all, hardly. Okay, so just to summarize that, too much water promotes instability. Very wet sand flows like a liquid. Excess water reduces cohesion. That cohesion is an important word. Cohesion is what holds the grains together. And excess water adds weight to the slope. Water supports some of the weight of overlying material, reducing perpendicular force on the slope and reducing friction that counterbalances activity. So when you put water in the mixture, it reduces, remember GP, it decreases GP, and the perpendicular force is less. And the perpendicular force is what holds the particle to the slope so it doesn't go down the slope. So GP is important if you want to go back and look at that diagram. I don't have a picture of it here, but GP is what sticks the particle to the slope. GS is what moves it down the slope. So an example is higher risk of landslides are in the Appalachian Mountains than in the western states where steep slopes are steeper. Well, why? We have more precipitation in the eastern U.S., and in addition of water to slopes with loose materials increases the likelihood of failure. So because you get more water and snow falling down in the eastern side of the U.S., you get more slope failure. For one factor. There's other factors too. Well, here's what we're talking about. You see a field at the top of the picture. Maybe it's some type of field in California, grapes or something like that. And then you get this city down below the slope. Well, what happened here is that you get people watering the field at the top of the slopes, and that puts more water into the slope material and decreases GP, or the perpendicular force that holds the slope together, and GS goes ahead and moves the material on down and buries those houses. So that's a problem. So who's at fault there? Well, going to have to be some discussion between the people at the field that are trying to grow the crops up there and how to manage the slope failure with the houses below it. Here's another example here. You got a slope failure. You got water being put in the in the slope above there, and because of that it starts to mass waste and move the material down. And there is the edge of where that mass wasting would start, but it would go ahead and creep back on uphill into that field where that tree is over time. Okay, so if we look at this, slope failure can be a disaster, and those poor homeowners. On the other hand, they really shouldn't have built homes to start with there, and that's a cold, calculated thing to say, but people really get in trouble because they don't think about geology. So if you don't get anything else out of this earth science course, I want you to think about exposing yourself to the factors that are around the earth that affect you, and where you build your house, and just the things that can cause you problems for you and your family if you aren't aware of them, because the developer that built that house sold us and didn't care. Okay, so here's Venezuelan landslides. Venezuela has had some big disasters because of landslides, and the mountains of the Sierra de Avila in the city of Caraballo, I don't know Spanish, Caraballo in the foreground, with the picture on the right of where Caraballo just had mud coming right down that valley, covering most of that part of the city. It's a horrible thing to happen to the city. Well, what happened in Venezuela? Well, you had a lot more water than you usually do. They had 36 inches of rain on the steep mountains. You had a series of floods and landslides from that unseasonable rainstorm, killed 19,000 people. That 3-day rainfall equaled the average annual rainfall in the Midwest, at 36 inches. Vegetation has shallow roots in the 10-foot thick soil and regolith, so the vegetation was not holding the soil. And cities are located in the flat patches of ground at the mouths of the narrow canyons, because that's easier and cheaper to build there. And if you don't have a lot of money, you build where it's easy and cheap. And so what happened is you had slurries of rocks and dirt that flowed down that mountain from up to 30 miles an hour. And you can see a man standing on a big rock there, because that 30-mile-an-hour slurry of dirt and rocks, and it carried rocks that big down the mountainside. Some more discussion about this disaster in Caraballo. You had single-story buildings that were totally buried. You had apartments that collapsed. You can see the edge of that apartment collapsed. It just got crashed into by rocks from this slurry and destroyed it. Couldn't evacuate people because the main road was covered over, and the damage, back in '99 was $2 billion. It'd be a lot more today. So poor city planning, poor construction standards, poor building inspections, and the city carries the price. Well, there's human influence that caused that. They don't have a lot of urban planning in Venezuela. In La Conchita, the town on the edge of coast of California that we looked at, you had overwatering of crops above the bluff. If you have deforestation, that can create slope failure, because then you get more water affecting the slope, because vegetation is not holding it back. And logging and forest fires can remove vegetation. So how many factors can you name that contributed to debris flows in Venezuela? Well, it certainly didn't have urban planning. and they had a lot more water than they would normally have expected, and there was less vegetation, and they needed to hold that back. So here's an example of another landslide slope failure. Well, how can we minimize slope failures? Well, if you've driven through Colorado, you've seen things like this, where you have wire nets that are next to the road to keep rocks from coming on down the road. You see signs to keep people from driving into rocks when they come on down the road and ended up on the top of the road. Or you can get retaining walls to hold the slope back. So physical restraints work. Here's a picture from one of those slopes. That looks a little bit scary if I were living down there. Here's another picture that a lot of these are from California, because California has lots of real thick regolith areas where you have unconsolidated dirt that's blown off the Sierra Nevada mountains and deposited on the edge of the coast, and then people build on it, and then they water their grass, and it just the slope fails underneath their house. From this picture, you see a landslide, and the house there is probably not in a lot of danger from that landslide or from another landslide. If you look at the slope above that, you notice that it's capped by a cap rock, and so anyway, types of slope failure. You have rock fall, and you see a picture on the left of rock fall. You have rock slides, and you have slump, and you have creep. Different types of slope failure processes. So let's spend some time talking about these slope failure processes: rock fall, rock slides, slump, and creep. Mass wasting is characterized by a type of material involved. Here's a rock fall. So you have a road that's shut down because rocks came off that cliff, and somebody's going to have to come in and remove those so the road can be driven on. And here you have a rock that came down a cliff and crashed into a cabin. It's a big rock. Creep is the slow, uniform movement of soil. And if you look at walls around town, you'll see lots of walls have creeped a little bit, so that the wall started out as vertical, but then with gravity, remember GS is the force of gravity parallel to the slope, it's going to move that a little bit, and here you get an example of creep affecting the way that tree is growing. The tree's grown down to the left in its early stage. And here you get a typical creep issue with a wall at the base of a slope of the house, and the water the grass and goes into the soil, and it just very slowly starts to creep downhill. That's really expensive to fix a wall like that, so you want to do it. You want to be aware of creep before you build a rock wall. And this is where a good example of earth science is very practical. So when you own a house and you have a hill, you want to be aware of creep as a way to keep yourself from having an expensive fix-it operation. Solifluction is the creep of saturated soil over permafrost. We don't have permafrost here, but if you lived up in Alaska, northern Alaska, you'd have permafrost. So it's the creep of saturated soil, i.e. soil that's saturated with water, full of water, over permafrost. And here you get an example of solifluction. Okay, slump is the slow or fast displacement of a block. And so here you have a piece of ground that's slumping down, and it can happen quickly or it can happen slowly. That slope failure we saw in Ch10, California was a good example of slump. In this case it happened fast, but it doesn't always happen fast. Okay, a slide is the movement of a block parallel to the surface. And so notice that the rock layers are parallel to the slope, and so you have one rock layer sliding down on top of another rock layer. A rock slide is a large-scale movement of rock traveling rapidly down a slope along a surface. And so here you have rocks. Notice the rock layers are parallel to the slope, and so you have rocks that are fall down from the upper right, and they're paralleling along that wet shale layer normally, which acts as a lubricant. So you have water that may it may rain, and then it goes down through the rocks in the top layer, and then it hits the shale, and because shale is impermeable, the water doesn't go through the shale, so it forms a lubricant, and it gets slippery, and the rocks on top of the shale slide on down and cover whatever they cover. And so here's an example of sandstone above shale, above limestone, and before the slide it looks like this, and then after the slide you get that slope failure where you have the rock slide slipping on down on top of that shale layer and dumps the debris in the valley. And it's going to happen again on up the hill too. Let's look at how a rock slide affected a dam in northeast Italy. There was a 1960 rock slide that affected that reservoir, and you see the dam on the left, so the water goes from the right to the left, and that slide filled in the end of that reservoir, which was a real problem because you had the dam that was needing the water from that reservoir. And there you can see a close-up of where it slid down the mountain and filled in the end of that. So you had this big dam, couldn't use the dam because the the rock slide had filled in the reservoir behind it. Now what do you do? If we kind of summarize what we just looked at, you see a point there where it shows a 1960 slide. Basically it happened at the side of the reservoir. And then a few years later, in 1963, you had a larger landslide that filled in the reservoir, which really created a problem for the dam. And so we have to be really careful with how we do engineering to be aware of the geology and understand what potential risks there are to what we build, which is why it's so important to know something about earth science in a whole lot of areas, because you may be the politician, or you may be the person, decision maker, deciding how to do something or where to spend money, and if you don't know something about this subject, you can end up wasting a lot of money. Well, one slope failure process is flow, which is, we just define that as it's fast. It's debris becomes fluidized by water or air. That's basically a fancy way of saying that it rained hard, the water gets packed, the soil gets full of water, and because it gets full of water, it can't hold, and it breaks away and runs on downhill. Mathematically, we'd say that because of the water in the soil, GP, or the perpendicular gravity, is decreased, so it doesn't hold the regolith to the land. And here's another example of flow where you got a heavy rain and it didn't hold. It looks like that's been deforested. And here you have another example of flow coming on downhill off the mountains up there, bringing mud down with it. That's a farming area. Finally, we see a type of slope failure process as a fall or an avalanche, where you have a free falling rock from a cliff, and it just falls as fast as it can because it's just free fall. And here's an example from Yosemite where the rock just free fell from on up the hill, and it's not where you want to be when that happens. And here you have a picture from Zion National Park of an avalanche coming off the side of that cliff.